Hi, this is a quick preview of our paper LeanVec, Searching Vector Faster by Making Them Fit. Today, vector search seems to be everywhere as it is powering RAG systems by adding long-term memory and factual grounding to LLMs. The dominant solution for performing these graph searches are graph-based indices, as they provide excellent trade-offs between performance and accuracy. The vectors used to perform these searches are produced by embedding models because they preserve the semantic similarities between the elements that they encode. However, these models produce vectors of high dimensionality, and this dimensionality is growing, and this is hindering the performance of modern graph-based indices. Our solution, LeanVec, uses dimensionality reduction and establishes the new state-of-the-art accelerating graph-based indices to new heights. It does so for two different setups: in distribution, where the queries and the database vectors share the same statistical distribution, and in the out-of-distribution setting, where queries and database vectors have different statistical distributions. The overwhelming majority of unstructured data is encoded using embedding models because they have outstanding capabilities to preserve the semantic similarities between their inputs. These models produce high-dimensional vectors, and the dimensionality of these vectors is growing with the increasing complexity of these models. Over the past 5 years, we have seen the average dimensionality increase from 500 dimensions to 1500 dimensions, with larger models using 4,000 dimensions or even higher numbers. This exacerbates the curse of dimensionality, where it is very hard to dissect the space to perform surgical searches and achieve great speeds for similarity search. The main consequence of this is that search speed suffers. When we were seeing dimensions in the low hundreds, we were observing speeds in the order of 100,000 queries per second. As we move to higher dimensionalities, we are seeing a tenfold decrease in search speeds. The main culprit here is the curse of dimensionality that forces us to do way more exploration to reach a target accuracy. This additional exploration involves computing more distance computations, which involves fetching more vectors from memory. Since these vectors occupy more space, then memory latency starts to become more meaningful, which slows down the overall search. To try to alleviate these problems, recently locally adaptive vector quantization was introduced. This is a scalar quantization method that sets the state of the art and reduces the vector by up to 4x while having a minimal effect on search accuracy and allowing to compute very fast distances. It is inscribed in the typical framework of performing search and re-ranking, where we do the search with heavily quantized vectors and then we do the re-ranking with residuals such that we can retrieve optimal accuracies. Although this two-level quantization scheme with LVQ achieves significant speedups with respect to uncompressed vectors, it is not sufficient to fully alleviate the problem in the case of very high dimensional vectors. LVQ compresses the vector by reducing the number of bytes per dimension, but we have another quantity, the dimensionality of the vector, that we can play with to achieve higher memory compression ratios. The problem with reducing the number of dimensions through dimensionality reduction is that in modern setting we encounter what we call out-of-distribution queries, i.e. that the queries and the database vectors do not belong to the same statistical distribution. This commonly happens in two use cases. One is when we are using multimodal search. For example, we are using text queries to fetch images. And we are also encountering this problem when different deep learning models are used to encode the queries and the database vectors. This often occurs with question answering, where different deep learning encoders are used for these two types of vectors, for the question and the answers. The consequence of this is that on top of the traditional loss in accuracy that we have when we're applying dimensionality reduction, such as PCA, in the ID case, we observe a 25% drop in search accuracy, but in the OD case, that drop in accuracy elevates all the way up to 40%. So we have to deal carefully with this new setting for achieving dimensionality reduction successfully for similarity search. In this work, we present our solution to this problem, LeanVec. LeanVec combines dimensionality reduction with scalar quantization via LVQ. LeanVec relies on the same search and re-rank framework that we saw for LVQ. The key difference here is that the graph search is conducted using vectors that have gone through a dimensionality reduction step and a scalar quantization step. Then the re-ranking step is performed using the full dimensional vectors to recover any accuracy that we have lost as a consequence of the dimensionality reduction and the quantization in the graph search. The key element here is that since we are conducting the graph search on vectors that have lower dimensionality, we also have to apply a dimensionality reduction step to the query. This step needs to be applied extremely fast in order to continue accelerating the search and not slow it down unnecessarily. So the combination of these features makes LeanVec a state-of-the-art method that achieves great acceleration with respect to the application of LVQ or the search conducted with full precision vectors. LeanVec is particularly designed for maximum inner product search, where we approximate the inner product between a query Q and a database vector X with a linear dimensionality reduction that applies projection matrices A and B to the query and the database vector, such that the outcome of these applications are vectors of lower dimensionalities. The application of the vectors to the database vectors can be done offline when we are constructing the index, so this is a less critical step, but as I was just mentioning, this dimensionality reduction or the application of the matrix multiplication to the query needs to be applied during search, so the speed of this step is extremely critical, and that is the main reason why linear approximation was used in this work. The projection matrices A and B that are used in our inner product approximation are learned from data in LeanVec. We consider the following optimization problem that takes into account all the inner product between a set of query vectors Q and a set of database vectors X. The projection matrices A and B are constrained to be row orthonormal matrices. When the set of query vectors and database vectors have the same statistical distribution, this problem is built in such a way that the resulting matrices A and B revert back to PCA behavior. When Q and X do not have the same statistical distribution, then applying a matrix A to the queries and a matrix B to the database vector, and these are different matrices, one from the other, makes it for the excellent performance in out-of-distribution settings. The structure of this problem is such that we can safely subsample the number of database and query vectors that we use for learning, and a very small number is enough to achieve very consistent results with respect to the structure of A and B. We have introduced two solvers to optimize this problem. One is based on a Frank-Wolf block coordinate descent algorithm, and it relies on a convex realization of the orthonormality constraints on A and B, and it comes with theoretical convergence guarantees. We have also introduced an algorithm that we call an eigensearch that finds the best convex combination of the covariance matrices of the query and of the database vectors in such a way that the objective function is minimized. This is an extremely fast algorithm. Both algorithms produce matrices of high quality, and they have different trade-offs, but in practice they behave very similarly to each other. We have implemented LeanVec in Intel's Scalable Vector Search Performance Library, SVS for short, and we can see in the plots below that the combination of SVS and LeanVec provides significant speedups with respect to the other alternatives. Because these advantages come from dimensionality reduction, they become more pronounced with higher dimensional vectors. So in the second and fourth plot, we can see the speedup that is achieved with LeanVec and SVS over phases IVF-PQ. And the second plot is the case with in-distribution queries. In that case, we have 8.5x speedup. And in the fourth plot, it's an out-of-distribution example where we have a 7.x speedup with respect to phases index. In the paper, we have included many more different experimental results. I will just provide a summary here. In the in-distribution and out-of-distribution query setups, we can achieve up to 3.5x faster search and 2.5x faster search respectively. These advantages become more prominent as the dimensionality increases. Also, we can build a graph with vectors that have been subject to our dimensionality reduction, and in that case we can build a graph almost 5x faster with no noticeable decrease in the quality of the graph. We have also compared to the LeanVec results with state-of-the-art transformer-based methods for dimensionality reduction, and we can show that LeanVec, while being linear, is at the same time faster and more accurate than these alternatives. Lastly, let me point out that the optimal dimensionality that we want to achieve with LeanVec depends on the system and the dataset, but 256 dimensions offers a very reasonable choice that works great across the board for many datasets and system configurations. So I invite you to take a look at the paper for more results and more technical details about our algorithm and our overall framework and innovations. Thank you.